Hello and welcome, guys. Today, this is Chahel here, and we are going to discuss the solutions of Codeforces Round 802 Division 2. As you can see, I could solve problems A, B, C, and D, and I would give my approach and the solutions for the same. Now, moving on, let's go to problem A. So, problem A basically gives us a table of size n cross m, where you have n rows and m columns, and each of the element has a specific value stored in it, which is basically increasing. If you see, like, they have made a table in each cell. So what they want us to do is that they want to find us the optimal path from the first element 1 comma 1 to m comma n, the last element, such that we can go only down or right, and they want us to choose a path such that the cost of the path is minimum. And that's basically it. And as you can see, they have given n and m as 10 to power 4. So n into m would be about 10 to power 8 maximum. And so they kind of expect a linear solution from us in terms of O of n and m, and not a quadratic or a solution in which we will check all paths. Now they have given some test cases. So after trying out some of the test cases, like say you can try out 2 cross 3, like you I urge you to try them by yourself if you couldn't solve uh, them in the contest. And so what you'll see, if you enumerate all the paths for 2 cross 3, the most optimal path will be the one marked in the figure, which basically goes through the first row and the last column. And now, what I basically like, if you try this for a few observations, like from for one cross n, it will directly be one. And if you say try it out a few times on a different test case, you'll realize a pattern. And basically, that pattern that I claim is that basically you need to traverse through the first row and then through the first last column, and this shall give you the minimum price. The proof of it will be as follows: that basically say you have this path that goes through first row and the last column, and say you make any modification to the path, that is like you go through this element or so, then this element will always, like this element, say in this case 9, will always be bigger than 5, and it will increase the cost of a path. Or to be more mathematically concrete, the cost of this element would be uh, roughly how much, like m plus n minus 1 time 1. Yeah, it will have a cost of m plus n minus 1, and that is definitely more than your m. And so your cost will keep on increasing. Like the cost of this element is m, the cost of this element is m plus n minus 1, and for n greater than 1, the cost of this element will be greater. And so the cost of a path will keep on increasing, and the most optimal path and solution for this is the path that goes through the top row and the rightmost column. And now basically we have coded the same, as you can see here. uh, so I have basically taken n and m as inputs, and then basically I've traversed through the uh, first row adding the sum, and then I've traversed through the last column adding the sum again, and then I've just outputted the sum. And that's pretty much it for the first problem. uh, then moving on to the second question. So the second question is palindromic numbers. Now this is an interesting question. So first they have given us like, so in this question basically what they want us is they'll give us a number as an input, and we need to give an output, a number, such that adding these two numbers would give us a palindromic number. So on first glance that might look trivial. However, there's an interesting thing in the question, that basically what they have done is they have given n is less than equal to 10 power 5. So n is the number of digits. So if you see even the, like, data size of long int, even long int can't store something like 10 power 19, 10 power 20, and they have given us 10 power 5 digits. And long int can store 1920 digits. So obviously they don't want us to take the input in form of an integer. Rather, they expect us to either make a character array or a string and take these numbers as an input character, and then we'll convert these numbers, these character, like they'll be in form of a character. So we'll convert them to their ASCII values, and which will give us the integer stored in those numbers. So the aim is basically to convert these into palindromes. So if any of you were stuck on how to take input, and now you got the idea of how to take the input, then I would urge you to pause this video and try the question again by yourself. So now suppose say we have taken the inputs. So as you can see, the input will have a size of n, and they want us to give a number which doesn't have any leading zeros. And this is very critical because say if they didn't give this condition, then we could just take 99999 n times and subtract that with this number, and we would get a number that would satisfy this. However, that might have leading zeros. If say we take 99 and the number will be 99, so we'll get 0, and that will have two leading zeros. So we need to avoid that. So for this, basically what you can see is like if you have any number as such of n digits, then we can make two cases, that the first digit is a 9 or the first digit is less than 9. So now, even now is a good time that where you can pause and divide these two cases and try to solve by yourself. Now say for the case where it's less than 9, so we can, in this case, we can directly take another array like which has all nines at all places of n digits, and subtract this number from our nines, and then output the result directly, and that won't have any leading zeros because the first number will be less than 9, and so the output first digit will obviously be 1 or greater. Now say the first digit is 9. Now this is unlucky for us. However, now that it is 9, so we can't take 99999. However, we can obviously take a palindrome which is of n plus 1 digits. Now, so for this, I propose that we take the palindrome 1 1, followed by about n minus 3 zeros, and then this. So basically, if you see, the length of this number is n plus 1 digits. Now, what we'll basically do is we'll store this in an array. So this array will be such that the first element has 11, rest these have 0, and these have 1 1, and we'll keep on subtracting like we do normally. And the thing is, whenever this number is smaller than the number that we are subtracting from here, then at that moment what we do is we'll carry over the number from the left hand side to the right hand side, and so on. We'll keep subtracting, and in the end we'll get an number, and we'll just output that number. So this is what we have implemented, and this is how I've done that. So yeah, so I've taken n as input, then I've made the character array here as you can see, and then I've created these two integer arrays to sort of convert the character array into integers so that we can manipulate with it. And then basically I've converted the character array into integer. Basically, see, this is a character, so you can typecast it using int bracket. This converts it to the ASCII value, and 48 is the ASCII value of 0. So if this is 0, this will give 48, and 48 minus 48 will give us 0 in BF5. Now this line is to ensure that basically we have made a token E. So whenever like this checks that the first digit is 9 or not. If it isn't 9, E will stay 1, E will stay 0, and if it is 9, then E will change to 1. Now if E is 0, then we are directly outputting 9 minus that digit, and that will sum up the question for us. However, if E is 9, E is 1, which is our unlucky case, so then we have created this C. C is the array that we'll subtract from. So, like as you can see, the first element is 11. All the middle ones have been initialized to 0, and the last and second last ones are 1. And then we have basically applied the simple fact like if it's greater, then we can simply subtract. If it's less, then we are doing carryover, which is the simple subtraction rule. And the first result we have handled separately by doing minus, and then we have just outputted the C of I, and that pretty much sums up problem C. And moving on, we can go to problem C now. So here we have problem C, helping the nature. Now, here basically what the question says is, uh, like Leon wants to control the moisture of trees such that the moisture of trees should end up being zero. And for this, like he initially gets a value of what's the moisture of each trees. There are n trees in the forest, and Leon can basically either increase the moisture of all trees by one, or he knows that there are trees from 1 to I, he can decrease their moisture by 1, or he can decrease the moisture of 1 to n by 1. So, and then basically we have been given these test cases, sample test cases, and the output, and we need to output just the minimum number of steps that he has to take. Now, an interesting thing to note in this problem is that basically the order in which you do the steps doesn't matter. Like if I water them first and then take out the moisture, or take out the moisture and then water them, that doesn't make a difference in the final output. And another thing is that basically we don't have to take any redundant steps. So, like adding and subtracting both shouldn't be done on the whole data set, and that's what you have to ensure. No redundant steps. So now just to like get the whole of it and how we'll solve it, uh, we'll solve a few test cases. I think this line hasn't gone. Or anyways, so first up we have the test case of minus 2 minus 2 minus 2. So what we can do in this is we can directly add plus 2 to each of them, as we can do that, and that would take us two operations, and we'll end up with 0 0 0. That was fairly trivial. Now in this one, the second test case. So what we can do is we can first check out the first two indices. So here if we see this is 10 and this is 4. Now any operation that say adds, that subtracts from all or adds from all, won't change the value of 10 and 4. And so we need something that operates on either 4 and 7 or 10. And as we need, if we would subtract 1 from 4 and 7, that would only increase the gap between 10 and 4, which we need to decrease. So what we would do is we would subtract 6 from 10, and that would make these two equal, which they have to be in the end. So we are doing that first, and after 6 operations we would end up with 447. Now we analyze these two digits. Now as we can see, 7 is the bigger number here, and they have a gap of 3. Now we can't add to all, that won't affect the difference of 4 and 7. And even if we subtract from 4 and 4, that would just increase the difference. So we have to subtract from 7, and so we'll subtract from 7 three times, minus 1, and we'll end up with 444. Now, an interesting thing that basically the moves that have been allowed to us are either increasing all numbers by 1, or decreasing 1 to I by 1, or decreasing I plus I to n by 1. And now we are ended up with 4 over 4. So in this case, an interesting thing is that if you take I equal to n directly, then basically what you're doing is you're subtracting 1 from all the numbers. So essentially we have been allowed to do that also. And so in 4 moves we can subtract from all the numbers, and we'll end up with 0 0 0. And as you can see, this took 13 moves exactly, as was specified in the test case answer. Now let us say we take the the second last test case of 4 minus 4 4 minus 4. Now, if we see the first two places, they again have a gap of 8 in them, and we need to minimize that. So, we would have to subtract it from the lower value, as we have done previously, and we'll have to subtract it 8 times because that's the gap between them, and we'll end up with minus 4, minus 4, 4, and minus 4. Now, we move on to the second and third index. They have minus 4 and 4. So now what we will do is as we can see, the 4 is the bigger number here. So we need to subtract from the right hand side. So we'll subtract from these two numbers, and we'll have to subtract 8. So what we'll end up with is minus 4, minus 4, minus 4, and 12, minus 12. Notice how even the last digit gets affected from what we do on the left hand side. And now basically we check the last two digits, and as we can see, the left number is bigger, so we need to subtract from that. So we'll subtract 8 from there to match it again, and we'll end up with minus 12, minus 12, minus 12, and minus 12. Now we can simply add 12 to all of them, and we'll end up with 0, 0, 0, 0. So in all we have taken 36 steps, and that's what was required in the question. And now if you'll notice, like from these test cases only, if you can come up with an idea, like these provide a good enough hint. If you can come up with an idea from these, I'll encourage you to pause this video and try to solve that. Else we can just continue on. And so as you can see, that what we are basically doing is, we are each time we are just comparing two adjacent values, and we are minimizing their difference, which we have to do eventually. And so we do it in the start each time, so that the order of steps don't matter. So what we'll implement is basically that we'll take the difference of both elements and we'll subtract it so as to equalize them, and we'll continue this process till all elements are equal, and then we just need to subtract. We just need to do as many moves as the value of them to get all zeros. And this is basically what I have implemented. So here you can see that. So I have kept many variables like n. Minimum is to keep a track of what's the minimum value, because as you can see, like in this case, 10 and 4, what we end up with is the minimum of 10 and 4. And in 4 and 7 also, what we end up with is minimum of 4 and 7. Even here, in 4 minus 4, what we end up with is the minimum of minus 4 and minus 4. Here again we end up with the minimum of minus 4 and 4. And here also we end up with the minimum. Hence, I'm keeping track of minimum so that it's easier to work along with the data. And then count here basically keeps a track of how many steps we have to take to do the thing. And RC is basically to count the number of times I've subtracted from the right side. So as you can see, this is basically to keep track of something like this. Like if anytime I subtract from the right hand side, like here, so what's happening is I'm subtracting 8 from here, but even minus 4 gets affected due to that. And as minus 4 is getting affected and it's becoming minus 12, thus we have kept a track of RC also, and that would basically do it for us. Yeah, and we have kept a track of RC also, and so basically RC would be 8 in this case, and this element gets subtracted by 8. So it's to keep track of that. And as you have to do it in O of n, thus I have just done it in one loop inside it. So first what I've done is I've taken a of 0 as an input, because I need to initialize minimum to a of 0. And then later on what you've done is take ai as an input, and then we have updated ai by rc, because as you can see, the right entries are affected by the number of times you have subtracted from the right. And then suppose ai is less than minimum, this means that the new element that we have encountered, say like for example we can do in this case minus 4 and minus 12, so the new element you have encountered minus 12 is less than the minimum of all the previous elements. So in this case, we'll have to subtract from the left hand side the difference of them, and that many steps will be added, and the minimum gets updated. So that is basically what you have done, that count adds the number of steps that you have taken, and the minimum gets updated. Now moving on, uh, if AI is bigger, that is something like this case, maybe like we have minus 4 and then 4. So in this case, what you are doing is we are subtracting from the right side. Like in this case, we have subtracted 8. So in this case, the right count gets increased by 8, or the difference between them, and the minimum stays the same, and the count increases by 8. So that's exactly what we have done here. Count increases and RC increases. Now, after we have done all the steps, if you see in the end, like in this case, we ended up with 4, 4, 4. In this case, we ended up with minus 12, minus 12, minus 12. So whenever we end up with something, what we are doing is we are just taking that many more steps, and that is the absolute value of what we are ending with, because we can do -1 to all and +1 to all. And so we have done that to add absolute value of that to count, and then we have just outputted count for this question. And that's pretty much it for the question C. It was a nice elegant question. If you see, the code is pretty short. Now moving on to question D. So this is a pretty interesting question. uh, Now what they have done is, basically in a city named Devando, there's a huge river lock system, and there are n locks, and each of them has a capacity of vi. And whenever a lock gets exceeded, so as you can see, it overflows into the next lock, and so on, and the last one gets overflowed to the river. So what we need to do is we need to fill all the locks within a time tj that they'll provide us, and we need to tell us the minimum number of pipes that we can open. Now, each pipe can be placed over any lock, but any lock can have maximum one pipe, and each pipe gives only 1 liter per second, as you can see here. Yeah, 1 liter per second. So, what? So we need to output the minimum number of pipes that we need for each query. As you can see, we have n 2 power 10 by 2 into 10 power 5 number of locks, and then each lock can hold up to 10 power 9 volume, and then we have q queries given of 2 into 10 to power 5, each having a value of 10 up to 10 to power 9. And if it isn't possible to fill the lock, then we have to output -1. And so basically what we notice is that a solution of say n times q, that will be 4 into 10 to power 10, won't work, because that will go above the number of operations that our computer can do. And so ideally we want something of o of n plus q, or something like that. uh, and so basically what we need is that for each query of time that has been given to us here, we need to ensure that we get the answer in a constant amount of time, not O of n time or something like that. Because if we end up doing that, then our algorithm will become O of nq, and that won't work. So that is what we have to ensure. And so for that, I think we need something like, we need to ensure that we can get the output very fast. And so for that, basically what I've done is, so now we move on to try out the test case. Say we try out this one, just to like get a few observations, and then we can move on to how we implement it. So yeah, so basically, for example, what's happening is we have all these locks with us, and say in this case, one trivial thing that we can notice is that how many ever locks we can have maximum that many pipes. So in this case, like in any case, we have maximum n pipes, and the amount of total water that we need to fill is sigma of vi, where as you can see, vi is the amount of water stored in the ith lock, ith wall. So we need to get vi amount of water, and say in the best case scenario that we have all the n taps open, even then this would take us a time of sigma vi by n, and this will be the minimum amount of time that we can fill it in ideally. So obviously if the answer is less than the statement, if the like query is less than the statement, then obviously we have to output -1. Now another interesting observation is that say in this case, if we take this test case only, if you do sigma vi, that turns out to be 15, and you have 5 locks, so that way your tmin will come 3. But the interesting thing to note is that the water can overflow only to the right hand side and not to the left side. So, and we have pipes, we can have only one pipe over each lock. So if we have a pipe of, so in the end what will happen is the first lock will have only one pipe, but we need to fill 4 liters on it. So that would take a minimum of 4 seconds. Thus, this Tmin of 3 seconds is kind of a lower bound, and a and 4 seconds is the minimum amount of time that this particular lock will take at least. And so for this particular case, any value less than 4 seconds should have an output as -1. Now another thing we can notice is that the worst case scenario, in which like we have only one pipe open, in that case it would take a total of sigma vi by 1, which is sigma vi amount of time. And this sigma in this sigma vi we can ensure that all the locks are filled. So what happens is basically if the query if the given time is tq, say, and if tq is greater or equal to sigma vi, then we can definitely say that the answer is 1, because 1 is the smallest number of pipes that you can open, and that's the minimum answer. Now, if we move on to the general case, say now we need to calculate how much, like they are giving us the time and we need to calculate how many pipes. So we can convert this question into vice versa, because basically what we need to do is they are giving us the time, we need to output the minimum number of pipes. But if you notice, we need to do this in O of 1 or O of log n or something like that. And to do that, basically, the thing is, if we do it directly that way, what we need is we need to know that if say we have 5 pipes open, then how much time does it take ideally. And so I think we should try to calculate like how much time it would take to fill all of them if we have k pipes open in n locks, and so on. So for that, let us try to do those cases. So one thing interesting thing that you would notice is, if we have locks like these, opening a pipe here and here, or opening a pipe here and here. So it's always better to open the pipe on the left side, because the amount of volume that it will flow in is the same only, because that it's fixed by the number of pipes that it will be. If we are k pipes, then k liter per second will flow, and we need to fill out sigma vi in all. And so it's ideal that we have sort of all the pipes on the left, because water can't overflow from right to go to left, so it always has to go from left to right. That's why optimally what we'll do is we will fill all the pipes to the left ones. So if we have k pipes, they will supply to the first k locks, and the next nk minus locks will get filled by overflowing from here. So for this, basically what we'll try to do is we'll try to find out the time, minimum time it takes to fill the locks with K pipes. So say we know this time for K pipes, and we need to find it for K plus 1 pipes, sort of something like that. So we have sort of many locks, say some n locks, and we have some K plus 1 pipes. Now basically if you see the as an intuitive approach, like if someone asks you this question, your answer might be directly sigma vi by k plus 1. However, as we can see that this case fails easily, like it fails even here if for k equal to 1. And even if we take something like this, like we have 4 in the first one and 1 in the second one, and one we take 2 pipes. So in this case you'll think that it's 5 4 plus 1 equal to 5 by 2, that will give you 2.5. However, you need minimum 4 seconds to fill the first one. So this, all the fields intuitive is not exactly the correct answer, like it's not the correct answer. But what we can notice is that, say what happens is the first k uh, locks. So in this much time we would obviously supply sigma vi amount of water to this lock system. Some of it might overflow, but if we can ensure that all of the left hand side gets filled, then we can say that all the locks get filled. So what we need to ensure is that all the left hand side locks get filled, and sigma vi amount of water is filled, because if all the left hand side locks are filled, mind you, so none of these are empty, and here also in the this lock also we have provided water, so this one should also get filled. And this way what will happen is the water has to go to the right, and for it to overflow, this lock has to be full. For that, all the locks in the middle have to be full, and this k plus 1th lock also has to be full. So essentially, all locks are full. So we have sigma vi amount of water. So no overflow will happen by that time if these locks on the left get filled before this time. However, if these locks don't get filled before this time, what will happen is there might be some empty lock out here, and these locks on the right side will be filled, but this one lock on the one or many lock on the left side won't be filled. So what we effectively need is, like, say we specify this by tk plus 1, the time taken to fill the whole thing if you have k plus 1 pipe. So this will be sort of maximum of the time to fill all these and the this time. So we can write this time as sigma vi by k plus 1, and let's denote this time by something like tt of k. Now tt of k is basically the time taken to fill k locks, first k locks with k pipes. Now basically we need to calculate tt and t of k plus 1, and that way our algorithm will work, and effectively what we'll get is, in the end, we'll store an array of, like, how, like, if we have one pipe, how much time it takes, two pipes, and so on up to n pipes, how much time it takes. Now if they give us any tq, that is any query, so if this query is like, see, in one pipe the time will be the, in, if you have all n pipes, then this will be tmin. So basically, if your tq is less than tmin, then it will come in this region and the answer will be -1. Suppose your tq is greater than this one or equal to this value here, tm. So in this whole region, we'll output 1 directly. So these two cases get covered directly. Now for any of the middle cases, what we'll do is, we'll find out, like, we'll start from the right side, and we'll find out the first value, say here t ti, such that ti is greater than tq. So what will happen is, in, if ti is greater than tq, then obviously in that many pipe, having that many pipes, we can fill up in tq time. Like, no, sorry, if ti is greater than tq, then this will be the first where, if we have these many pipes, then we can just not fill in tq. However, if we have these many pipes, then we can fill in less than tq time or equal to tq time, and basically this, the index of this will be what will output as the minimum number of pipes required. And this is basically what we'll implement, and this will roughly take, like, see, we have q queries, and as this array is sorted, we'll only have to do a binary search to find the such a ti. So it will take q ln n time, which is sort of n log n on q log n, as because both of them are 10 to power 5, and this code would roughly work. And this is what we have basically implemented. I have implemented, as you can see. So yeah, here. So I've taken this tmin will be the minimum time, as we said, to fill in. We've taken it as int min, and I've taken n, and vn is the volume of the array to store the volume. SV of n is basically the prefix sum. For those of you who don't know prefix sum, it is basically the sum of all the elements on left of an element. So like SV of I will be s all sum of all the vi's, all the vj's till ith element, and tt of n, as I have described in the example, is basically the time taken to fill first k locks by k pipes. And then pt of n is basically a vector that I've created that will store the minimum, store the amount of time it takes to fill a pipe with k pipes, like the kth element of it will be that. So I've taken the input of vi, then I've just this is basically how I've created the prefix sum, like the first element will be the first element, and every element will be a sum of all the elements on the right left hand side of it. Then what I've done is this is basically to calculate the minimum amount of time to fill all the locks. So SV of I will be, if it's ever greater than t min into I plus 1, basically like we have all the pipes open in the best case. So in that case, SV percentage I plus 1 will be, if it's 0, then we directly update it. If it's not, then we add 1. This is basically to account that the division in C++ is integral. And say we have I equal to 0, that's the first case. Now we are basically using this whole portion to initialize our array ti, like fix the values of tti. So this will basically do is, for the first element, it will directly take the first volume by I by 1 to give the tt of first one. And for any later element, this is basically done because there are, for the first element there are no elements on the left, so you don't have anything to compare it with. However, in any of the later elements, what we have done is we have taken the maximum of SV of I and TT of I minus 1. So TT of I minus 1 will be the time taken to fill all the locks on the left, and SV of I by I plus 1 is the time taken to give enough volume to fill I locks. So we are taking the maximum of both times because that's how we are going to iteratively generate it, and that will be TT given for us. Then now just we need to calculate, after now that we have calculated tt, we need to calculate our pt, that is basically the this array elements. So that will tell us the amount of time it takes with k pipes, and that's what we are doing in this loop. So what we have basically done is we have calculated a time dt, which will in essence be the time it takes to fill up to like fill all the locks with I pipes. As you can see, like this is the time taken to fill all the locks by I pipes. SV of finance will be sum of all the I elements, all the n elements. So that's essentially our sigma vi as we had shown in the Jamboard. And we are dividing that by the number of pipes that are open to get dt. And the max of these two will be the time it takes to fill up that many pipes, fill up minimum time it takes to fill with that many pipes. Now that we have all of these, now we just take in the queries, the number of queries, and we run in the loop each time. So tq will be the time given in the query. As we had shown, if it's less than t minutes, then obviously it's minus 1. We can't fill it so fast. If tq is greater than sv of I minus 1, that is, it is greater than the amount of time it takes to fill with one pipe, then we'll output one pipe because we can do it in one pipe. And then now we have created an iterator for the vector, and this what it does is basically we are using this inbuilt function upper bound because inbuilt function in C++ are very efficient, and what it will do is it will basically return the first element whose value is just greater than tq, and we basically use that as we have shown with the plus one to output the number of pipes that it takes to fill in that many things, and this will give us the minimum number because upper bound returns just the greater value, and we have effectively done this in O of QLNN, and as you can see, that's why it matches the inputs constraints. I hope you enjoyed the tutorial, and be sure to share and subscribe, and please put any comments or any queries or any suggestion that you have in the comment box, and feel free to hit me up. Thank you.